This video deals with finding analytic expressions for the energy and angular momentum of a massive particle orbiting a Kerr black hole in the equatorial plane. It covers both the prograde and retrograde geodesic cases for stable circular orbits. So let's imagine we've got a laboratory, or a particle, let's say, of mass small m, containing an observer, and he or she is freely falling in the equatorial plane of a Kerr black hole. And the Kerr black hole here of mass big M. Now, in order to follow a circular orbit at some chosen fixed distance r, we need to know the angular momentum h and the energy parameter epsilon, which is the energy of the particle over its rest frame energy. So that's the energy of the particle in its orbit, capital E, and this parameter is the ratio of that energy to its energy in its rest frame, far from the source mass. Okay, we need to know some other things, but they're the two things we'd like to be able to find out. And for a given distance u, as you'll see, which is the reciprocal of the radius r, for some fixed distance, what angular momentum does this laboratory massive particle, whatever it is, need, and what energy? Okay, so an example of a massive particle in a circular orbit, we've covered this in a previous video with the Mathematica notebook and simulating it. And for some particular values for the angular momentum prograde, so co-rotating with the black hole, its energy is set to this value here, negative this quantity, and it's set at some distance of 19 gm on c squared, and it produced this circular orbit here. So circular orbits are possible for select values of the angular momentum and the energy. Now, stable circular orbits occur at the minimum of the effective potential, and if you set the energy to that point, then that's where you're going to find the stable circular orbit. So there are, for any given circular orbit, there's a particular angular momentum and particular energy that you need. All right. So let's start with the equation that governs the radial motion in the equatorial plane. So here we have this kinetic term, this effective potential term, and the total energy here. All right, now for circular motion, we require r dot to be 0 because it's a fixed coordinate. It's at a fixed radius, and so the change in that radius has to be 0, so r dot is 0. So that deletes for us the first term, sets that to 0, and we're left here with the effective potential is equal to the total energy. Now this is where we're going to get circular orbits. Now the question is, are they going to be stable or unstable? We'll address that later on. But here the effective potential depends on the mass of the black hole. It depends on the mass of the object, the laboratory, the massive particle, whatever it is, that's little m. The mass of the black hole is capital M. It's going to depend on its distance from the source mass, capital M. It's going to depend on the angular momentum of the massive particle, laboratory. The A is the spin of the black hole, the speed of light. Epsilon is the energy parameter I mentioned earlier. Okay, and they're the things that determine the form and shape of the effective potential, and it's that effective potential we work with to locate the stable circular orbits. Okay, there's one other condition we require, as you can imagine, that the acceleration of the radial coordinate is 0 as well. Okay, and we've seen that in previous video, mr double dot is minus the total derivative ddr of the effective potential, okay, which is this object here. Okay, so if we took the effective potential, this one here, differentiate that with respect to r, we have this object here. Okay, then we have the negative out front, and we set that to 0 as well. So in effect, we have now two equations. This one, r dot is 0, deriving from r dot is 0, and this one deriving from r double dot is 0. Okay, we then multiply this result, that's the second one, by r squared. Okay, so it gets rid of the r squareds underneath here, just leaves us 1 over r here, 1 over r squared here, still equal to 0. Now we make the substitution. It's easier to work with u as 1 on r instead of 1 on r. As you'll see later on, it does make things look easier to understand and deal with and to manipulate. So substitute into the first equation, that was the energy one, previous page. That's the effective potential plus is equal to the energy. That's this one here. We're substituting that in. We get this. Okay. Then multiply through by m to cancel this out. Gives us this object here. All right. Now, if we differentiate this equation here with respect to u, we end up with an acceleration equation the same as the one above, but just now in terms of u. So let's differentiate both sides with respect to u. You can see on the right hand side it's going to go to 0, and then over here you'll see the order of this will be reduced. That'll come down, u squared will come down, u cubed will come down 1 degree, and we end up with this object here. Okay, well, why can we do this? What was the point of that? Well, setting the derivative of the effective potential with respect to u equal to 0, that's what we've got here, implies that dV effective potential dr, the derivative of the effective potential with respect to r, is 0, because from the chain rule, dV dr is dV du times du dr by the chain rule. So if dV du is 0, then so is dV dr. So we're quite happy with that, because, and that's important because remember how dV dr was helping us locate the minimum of the effective potential, which is where we know these stable circular orbits exist. So keep that in mind for the rest of the video. Okay, we now have two equations. This one, the energy one, and then from the acceleration variable, we've got this one. Okay, now we're going to make a substitution, and we're going to replace this h minus amc epsilon, the angular momentum of the massive particle, and the energy parameter of the massive particle. We're going to replace this with the variable q, capital Q, that goes in there. It'll just help us to manipulate this object, work with these two equations here, and then we can come back and substitute h and all of this in afterwards. So having a look at that, well, rearranging this, we can have h squared is q plus amc epsilon all squared. Expanding that out gives us this object here. Okay, now we know what we can, h minus amc epsilon, we'll put a q in there. What are we going to put in here? Okay, well, we can rewrite h squared minus all of that. So that's this part here, this term here, part of this term. With this, that's h squared, which is all of that. So there it is, h squared, minus this object here, which is minus a squared m squared c squared times epsilon squared there. Then plus this times 1, there's that bit on the end there. And when we do that, this and this cancel, and we're left with this object here. Okay, so we now have an expression for q. We've now got an expression for this involving q's. I'll move on. Okay, now at this point, I'll just interrupt a bit, and we'll have q squared point out. We need to point out that q squared has two values according to whether h is positive for prograde orbits, that's co-rotating with the black hole, or negative for retrograde orbits, that's rotating against the rotation of the black hole, counter-rotating. Okay. In the prograde case, h is plus, and we expand all this out to give us qp, subscript p squared is all of this, there's a minus there. And for the retrograde, h is minus. Okay, now if we just work that a little bit, we factor out the minus 1 inside the total parentheses squared. Well, that's just plus 1. Then expanding that out, and there's no minuses, it's all plus. So qr squared is larger than qp squared for the same values. Okay, so just bear that in mind, because one is prograde for q squared and one is retrograde. We're talking about the particle laboratory rotating with the source mass, prograde, or the laboratory particle rotating against the source mass. So counter-rotating. Okay, so we have our two equations here, label them 1, label them 2. Now what we're going to do is multiply the first equation by 2, that gets rid of all those halves there. Okay, and then the second one we're going to multiply by u. Okay, so they'll get u squared there, u cubed here, yep, and a u here. All right, so when we do that, we end up with these two, 3 and 4. Next thing we can do is subtract equation 3, the first one here, from equation 4, the second one. So subtract this from the second one, or the second one minus the first one, or equation 4 minus equation 3. When we do that, we end up with, well, these bits, this middle term on both sides here will cancel out, and we will have one lot of gm u squared minus g m on c squared times all this. This bit on the right hand side will become negative. All right, so looking at that, and then the rest is a little bit of rearrangement. We'll get this m squared c squared epsilon squared by itself, like that. What we'll do is we've got a gm on c squared here, so we'll do the same also over here. So we'll have a gm on c squared here. That'll be handy later on because I'm just going to replace that with the letter or the variable mu, just to make it easier to work with, as you'll see shortly. All right, so this gives us the energy parameter squared, and then times these constants, little m squared and c squared. All right, next we'll rearrange equation 2 from earlier. I won't flick back to that. That's to give us this object here is this. Okay, we'll put that in there like that. And then what we'll do is we'll square all of that. So we have 4q squared, a squared, m squared, c squared, epsilon squared, u squared is this right-hand side here squared. Now, from the subtraction mentioned earlier, we could also do a m squared, c squared, epsilon squared times u squared for that as well, which gives us this. Okay, and then we can multiply this by the 4q squared, a squared. Okay, and so what we end up with is this object here. And bear in mind that this must equal this object up here. So a little bit of algebra, a little bit of combining equations here, but this object here equal to this, and this object here equal to this. Well, these two things are the same, so that and that must be equal. Okay, so we can form the equation. Here we go, this. What we're going to do is treat them now separately. Let's expand out the left-hand side. So expand out the left-hand side here, collect like terms, we end up with this object. Now we're going to expand out the right-hand side. Here it is. Expanding that out, we get all of this. Okay, and then equating the two gives us this one here. That one is equal to that. As you can see, it'll be easy if I make a substitution for the gm on c squared, which I'll do. Now, what we need to do, we've set the equation here equal. We need to collect like terms. We've got a q4 on the left, a q to the power of 4 on the left, q to the power of 4 on the right. I've got a q squared on the left and a q squared on the right. Can we collect them all together as a single equation? So bring everything over to one side. So let's do that. And we'll take all the stuff on the right here over to the left. And what we'll end up with is this first term here minus this first term here. Okay, and that'll give us this. When we factor out common factor of a u squared there and a q to the 4. Same thing here. This q squared comes over here and joins this one. And then this term gets left on the end by its own over here. So we now have a single equation. We could again save a bit more room and make it easier to look at and to keep track of the variables if we just make the substitution mu equals gm on c squared. So that leads to this equation here. All right, that's where we are now. We're going to be solving this quadratic for q squared. Remember how we referred to q squared before? There were two values for q squared, the prograde and the retrograde. All right, so using the quadratic roots formula, which I'm not going to include every single step here, I went to a software package to make sure it's accurate in doing it, and then simplifying. So from the software package, we get the first line here. And then what I need to do now is tidy this up. So that's our next step here. So these c to the 4, m to the 4, so we can take those outside, c squared, m squared, take out a factor of a here, which when we take it outside, these parentheses becomes a squared, which then when we take it outside the square root becomes a. We can take a u squared from u cubed here, and the square root of that is u, so we end up with u there. Then we've got this object here. Okay, we don't need to stop there. We can factorize the bottom there. By playing around with it, you're going to end up with this object here. Again, checking that on the software package. Next step here, next one down is we can also take out this square root here, which we'll do just down here. Did I tidy anything up here, or have I just repeated myself? Oh well, I appear to have repeated these two lines. Oh, well, unnecessarily took up space. Okay, anyway, we can take out this in the parentheses squared outside the square root sign, so it gives this object here. Okay, over this. Next thing we do, see how we've got a minus down here and then a minus here. What we do is we're going to take that out. So we're going to multiply through, because you're just dividing by -1 everything along here. So we're just going to change that becomes plus here and plus minus here over here. Okay, and that's what we've got. That's where we're up to at the moment. Now let's have a look. How can we simplify this? All right. Now, as I point out, there are two values for q squared. They are prograde, qp squared, and retrograde, qr squared. So qp squared is this object, and qr squared is this one. Okay, so the prograde orbit has the minus here. Retrograde orbit has the plus here. Okay, this task now of simplifying. Well, can we get down to something similar? Well, there is a textbook. Relatively physicist, but and they quote some results. So let's have a look at how we could get those results. Now, there is a simpler solution, not simply, but a simpler solution that results from cancelling terms according to their magnitude. There are some terms in here which are very, very small and some which dwarf others. Okay, so to use an example, and I've tried this example with a 1 billion solar mass black hole, but I've also tried it with 100 solar mass black hole. Anyway, for the 1 billion solar mass black hole, mu is this value here, 10 to the 12, and it's by far the largest value of all the parameters up here. If we set a distance, just for argument's sake, r equals 8 mu, we get this of the order of 10 to 13. U is 1 on r is of the order 10 to the minus 14. Now, u squared is of the order 10 to the minus 27. So anywhere you see a u squared up here, well, its value is of the order of 10 to the minus 27, very close to 0. Let's pick another 3 u mu gives us 0.375, square root of u mu up here, 0.3536, small. But u times mu squared is of the order of 10 to the 11. 2a square root u mu is of the order 10 to the 11. A squared u is of the order 10 to 11. A squared u squared is of the order of 10 to the minus 3. Okay. A squared u squared mu is of the order 10 to the 10. And this here, as you can see, is of the order of 10 to the minus 2. And again, this one 10 to the minus 2. So that terms that are minuscule compared to mu on its own up here, this 3u mu, 0.375, actually I need 3 u mu squared. Well, u mu squared is order of 10 to 11, so that stays. But there are some other terms up, like this a squared u squared. Well, a squared u squared here, that's very small compared to mu. So there are some terms that can effectively drop out. Okay, we can simplify the above by cancelling out the small terms and only including those that make a significant contribution. So the ones that make a significant contribution for q squared are the ones in red here. This one, that one, and that times that. They make a significant contribution. Okay. The others, a squared, u squared, 2u mu times this, drop out. U times mu drops out because this mu by itself is of the order of 10 to the 12, whereas these others are like 10 to the minus 2 or something. So, I mean, huge difference. Now, we're really only concerned with terms in effect that are, if you notice, that are first order, the mu, the a squared times the u, the a squared enlarged the u. So in a sense, just as your pattern is, you want to look for the first order terms. This square root u cubed mu is tiny, you don't want it, okay? So we also, in the denominator there, we don't want two factors of this. And then you expand it out and you've got these powers of terms, which again are very small. So you really only want one of these. Okay, so if you cancel out the terms in black here, drop them, simply drop them because they're very, very small compared to the other terms in red. You end up with this c squared m squared times all of this. And then we'll just take one factor down the bottom. We'll put in both signs here because you can have minus this and you can have plus this and they result in different values. So we include that in with a minus plus. Okay, so what we end up with, if we factor this further, factorize it further, we end up with cm squared here, and we have a times square root u plus or minus square root u. Okay, now if you expand that out, you'll get a squared u, and then 2 times a square root u times square root mu there, then here plus mu. Okay, we'll just keep down the bottom though these two terms here, because remember q's got to give us two values. It's got to give us the prograde case and the retrograde case. So this gives us two solutions. Okay. Okay, so here we go. Remember, the plus case was the retrograde and the minus case is the prograde. Just remember that. Remember, plus and minus up here, but minus plus down underneath. Okay, now q, when we take the square root of that, gives us two values. Q is plus or minus this. This is important because this relates to stability. Okay. And I'll talk about that later. I'm coming to that later. I'm going to be looking later on the minus case only because that's the stable case. The plus case is the unstable. Now, unstable means you can't maintain a circular orbit there. Small perturbations just carry it off. All right, so prograde and retrograde directions give this. Okay, retrograde was the plus, prograde was the minus up the top, and then opposite sign underneath. Okay, now next we seek the energy of our laboratory particle in its orbit, so we're after that energy parameter epsilon. Now earlier we found m squared, c squared, epsilon squared was all of this. All right, and that, if we now substitute in our q squared value in here, we get mu here times q squared times u cubed minus all this over here. And then we're looking here, common denominators, and then expanding out. With the common denominator here, we're going to have a u up top here. All right, and okay, actually what we'll have is that u there will cancel with that u cubed to give just u squared. All right, and this, yes, sorry, my fault. That u there cancels out a u from here, so we end up with u squared at the top, and that's where that u has disappeared to. The mu here is over here, and as you can see, single denominator, everything on top now. Next thing, let's work this through. On the previous slide, we had c squareds, m squareds on the left here and on the right, so I've cancelled those out. They're not necessary at the moment. So what's telling us now is that epsilon squared is not dependent on the mass of the laboratory. The energy parameter of the laboratory doesn't depend on its mass. Okay, it just depends on the mass of the black hole, the spin of the black hole, distance, and that's about it. Yep. Okay, and also the value of c, which is hidden in the mu there. But it doesn't depend on the mass, its own mass. Okay, so let's work all this through. Let's expand this out here. Okay, expanding that out again. Keep going here. Okay, over here. And if we keep going down again, we'll notice that here we've got minus mu u and minus 3 u mu. So that comes over here to be 4. We have plus or minus 2 of this and minus plus this. So they're coming down here. And we have here, I've got the a squared u cubed, which came out of, here we go, where do we get that? Good question. Oh, I can't seem to find it at the moment. Oh, sorry, right up the front, sorry. A squared u cubed mu, okay, and we get some of these terms. Now, u squared and mu squared, and we've got 3 of them here, so they're combined to make 4. So couple of terms have combined, giving us this object here. Next thing here, we'll look at, pull this over to here, which was this final one. Where is it? Here. Okay, well that comes down here. That went from, where did I find that up here? Okay, that went over here. And that goes there. Then these here are combined. Now, this was a little bit tricky. It took a while to work this one out. But you get 1 minus 2 lots of, if I factor out 2 from the second and third terms here, I get this. And then notice here with this thing that if I take this plus or minus this and square it, I can get this. So factorizing this is this. And it was a lot of playing around to get it. Denominator underneath, it has this form here. And then what we can do is with this, you can think of this as a plus b all squared, which will give you a squared plus 2ab, or minus 2ab plus b squared. So if a is 1 and minus this is b, so a minus b, square all that, you'll get a squared, which is 1, minus 2 times ab, a is 1, b is that, and then plus b squared. So it actually works out that way. So we end up with this object here for epsilon squared. Next bit. Finally, the value for epsilon is just take the square root of that. Gives us this object here. Okay, as before, the upper signs correspond to retrograde orbits and the lower to prograde orbits. Okay, the energy of our laboratory particle is E, the energy is E, and that's equal to the energy parameter times mc squared. Okay, mc squared is the total energy of the laboratory particle in its rest frame far from the source. Okay, and then epsilon is a parameter, whatever it is for that particular orbit. Now, the angular momentum h of the laboratory particle was contained within the substitution q equals h minus amc epsilon. Okay, now, and note that q has 2 values with negative corresponding to the stable circular orbit case. Because remember, this was deriving ultimately from the energy equation, and we took the derivative of that and set that to 0. And when solving for that, you're going to find the location of the minimums, and the minimums of the effective potential is where the stable circular orbits are. So we're going to need the negative value for that. The positive will give you the maximum, which is the unstable region where you can't maintain circular orbits for the simple reason they're unstable. Okay, so that's the difference of stability. We're looking at that more in a future video. But just the moment, the negative is the stable case. All right, so h then, because remember we had q equals h plus am c squared, and so h was q h minus, wasn't it? Sorry, my fault. It was h minus am c epsilon squared. Yep, there we go. And so h is q plus this. Well, let's put q in here for the stable case, the minus here, and then amc epsilon here, and we're going to have to work all this through. So we've got a minus here like that. When we work that through, well, common factor of cm can come out the front, so I'll just put that out here. Then we've got a minus a square root u, and then this minus sign multiplied by plus minus flips that to be minus plus, the mu there. And now, but minus a times square root u, plus over here, we have a times square root of u times 1, so that's plus a times square root of u, but that third term cancels with the first. Now that's true for the stable case. In the unstable case, they add together and reinforce, they don't cancel. So you got, in the end, you're going to have an extra term. For the unstable case, sorry. For the stable case, these cancel. First and third cancel. You're left with 1, 2, 3 terms down here. Okay, both minus plus here. Down we go. There's our denominator, square root of u times all that. And notice here we've got minuses on top, pluses underneath. Okay, so take that out front, and we have minus plus cm this. Okay, so this is the stable case. This is for stable circular orbits. And so the minus sign corresponds to the stable retrograde orbit, that's counter-rotating with respect to the black hole, and the plus case corresponds with the prograde or co-rotating case with the black hole. So the laboratory is rotating against the spin of the black hole, that's minus h, and the laboratory is rotating with the spin of the black hole, that's the plus case. And that's the difference. That's what these plus and minus signs are referring to. All right, next bit. Just notice when we factor out this -1 plus here, this one, they change the other side. That changes to plus. When you go through, so minus all this, makes all that minus, plus all this, you get all positive, except the negative on the end. All right, now, next one. So in summary, for a stable circular orbit at some fixed value of u equals 1 on r, the required energy E is equal to epsilon times mc squared, and angular momentum h can be found analytically by using h is approximately minus plus this, and the energy E is the epsilon parameter times mass times c squared, the mass of the laboratory particle. Just remember the effective potential varies according to the combination of the angular momentum of the particle, the energy of the particle, its distance from the source mass, the mass of the source mass, and the spin of the source mass. So change any of those or all of them and you get different effective potentials every time. Okay, but for a given black hole of mass big M and spin parameter A, okay, and for a given distance 1 on r, then you need this angular momentum for your laboratory and this energy for your laboratory or massive particle, whatever is going into a circular orbit in the equatorial plane. Okay, that's that.